Welcome to The Explainer. Today, we're going on a trip. And I mean a massive, mind-bending journey. We're going to start right at the measurable, concrete limits of our physical reality, and then we're going to zoom out straight into the infinite madness of the multiverse. We'll be looking at exactly how modern physics arrived at the frankly staggering conclusion that our entire universe might just be one tiny microscopic bubble in an endlessly boiling cosmic fractal. So, let's jump right in.
Okay, to kick things off, we have to talk about the sheer scale of our observable universe. Imagine a sphere spanning roughly 93 billion light-years across. That is the absolute limit of everything we can currently see, touch, or measure. It's a distance so unimaginably vast that even light, literally the fastest thing in existence, takes billions of years just to cross it.
And this giant bubble is packed with real, measurable data. We know, for instance, that it's almost 13.8 billion years old. We've calculated that it contains about 1.5 times 10 to the 53 kilograms of ordinary mass. But here's the crazy part. If you take all of that energy and spread it out evenly, the total density averages out to just about 5 single protons per cubic meter of space. So it's unfathomably huge, but also incredibly, incredibly empty.
Now, right off the bat, we need to clear up a very common misconception. There is an absolutely critical difference between the entire universe and just the observable universe. They are not the same thing at all. The observable universe is just a spherical boundary dictated by how far light has had time to travel since the Big Bang. It's not a physical brick wall out there in space. It's simply a horizon of visibility. It's the limit of our vision, not the limit of existence.
So, since our observable universe is really just the specific patch of space from which light has actually had the time to reach Earth, it naturally begs the ultimate question. What exactly lies beyond that edge? Like, if we could somehow teleport instantly past that 93 billion light-year boundary, what would we actually find? Well, let's look at how our theories about this have evolved. Historically, scientists relied on the cosmological principle, which basically assumes the universe is globally uniform everywhere, just more of the exact same stuff forever. But between the early inflation theory in 1981 and the string theory landscape in 2003, that whole idea was totally turned on its head.
To really grasp how we got there, we have to talk about eternal chaotic inflation. According to physicist Andre Linde, that super-fast early cosmic inflation didn't just happen once and then stop everywhere. No, it's an eternal, constant mechanism. Think of invisible energy fields permeating all of space. Quantum fluctuations cause these fields to randomly jump and freeze in place, which actually causes space itself to eternally self-reproduce. It's a runaway process where the universe is endlessly expanding and creating new space.
And this is a massive paradigm shift. Forget the classic expanding balloon analogy we were all taught in school. Our universe is actually more like a mutating, multicolored fractal of eternally boiling pocket universes. As inflation goes on forever, it constantly pinches off these little mini-universes. And here's the kicker. Each one might actually forget the genetic code, or the fundamental physical laws of its parent universe.
So why is this fractal idea such a game changer? Because it actually provides a beautifully elegant solution to a massive headache in physics called the fine-tuning problem. For decades, scientists have been completely puzzled by the fact that our physical constants, stuff like the mass of an electron or the strength of gravity, seem suspiciously perfectly tuned to allow human life to exist.
Just think about how delicate this balance really is. In different bubbles of this eternal fractal, fundamental properties could take on radically different values. If the cosmological constant were just a tiny bit larger, space would expand way too fast for galaxies to ever form. If the proton mass changed by even 1%, life as we know it would be literally impossible. Even our four-dimensional space-time is a strict requirement. In other dimensions, planetary and atomic systems just become entirely unstable.
By 2003, physicists realized that this mechanism of eternal inflation, combined with the string theory landscape, creates an incomprehensible variety of these universes. The math actually suggests there might be up to 10 to the 500th power of these vastly different environments. That's a 1 followed by 500 zeros. We're talking about an endless ocean of pocket universes, and practically all of them are totally hostile to life.
Andre Linde actually had a pretty great joke about this. After enjoying some free meals at a Cambridge symposium, he quipped, "The inflationary universe is the only lunch at which all possible dishes are available." Eternal inflation is essentially a cosmic free lunch. Absolutely every possible set of physical laws, every weird permutation of dimensions and masses is on the menu somewhere out there in the fractal. And that brings us to a profound but honestly remarkably simple idea, the anthropic principle. Because every possible dish is available out there, we naturally find ourselves in a bubble that's perfectly tuned for life. It isn't magic, and it's not some suspicious coincidence. We simply couldn't exist in the overwhelming majority of those hostile bubbles to even ask the question. We're here because this is one of the very rare places where here is even possible.
But, of course, this introduces a massive mathematical headache. When eternal inflation creates infinitely many universes, dealing with infinities makes calculating the probability of literally anything incredibly paradoxical. Cosmologists call this the measure problem. Basically, how do you define what's probable or improbable when every single thing that can happen happens an infinite number of times? To explain this measure problem, physicists use a kind of wild analogy. Imagine an infinite universe filled with infinitely many normal rooms where you can breathe perfectly fine. But because it's infinite, there are also infinitely many bad rooms where bizarre quantum flukes occur. Imagine a room where all the oxygen molecules suddenly decide to huddle in one single corner, leaving you to suffocate. Because of infinity, both types of rooms exist in infinite numbers.
If you try to endlessly compare those infinities, mathematically, 50% of all rooms seem uniquely bad, which obviously completely contradicts our everyday reality. We aren't all suffocating from quantum flukes. So, physicists resolve this by severely restricting their math. They only make predictions about the specific environments an observer can actually verify. Because we are here observing it, we have to trust that standard thermodynamics prevail locally.
This whole mind-bending realization of local versus infinite realities actually loops us right back to Albert Einstein. Einstein had this deep, famous faith in the underlying simplicity of nature. He firmly believed that there are no truly arbitrary constants in physics. He thought a single, beautiful, logical framework dictated all the laws of reality.
The fascinating thing is, the multiverse theory doesn't entirely disagree with Einstein, it just shifts our perspective. We have to accept that what we've always thought of as universal fundamental constants, like the cosmological constant, might just be local environmental parameters. They aren't the overarching laws of absolutely everything. They're literally just the local weather in our specific, life-friendly pocket of the multiverse. Our giant 93 billion light-year observable universe is essentially just one random sample in an infinite dataset.
Which leaves us with one final, absolutely staggering thought to wrap up this explainer. The next time you look up at the night sky, realize that the billions of galaxies you're seeing are just the microscopic, absolute center of our local bubble. Is everything we have ever known, our entire 14 billion-year history, merely a single, perfectly tuned glitch inside an endlessly growing, endlessly boiling cosmic fractal? It is a wild, awe-inspiring thought to leave you with. Thanks for exploring this with us, and as always, keep questioning the universe.